welcome again. Um, so in this session, I want to talk about evaluation methods for development interventions. So by development interventions, I mean any kind of a program which has got certain objectives in terms of alleviating poverty, improving the human capital base, skill development. So these methods are relevant in the context of any kind of development interventions. So now I know that all of you are highly trained economists, and most of you will perhaps already be familiar with many of the methods that we are going to discuss in the course of this session. So from an economist's point of view, the challenge is really not in mastering these techniques. You're perhaps already familiar with these techniques. The real challenge is in applying them in field conditions. So in the context of actual program implementation. And what you will generally find is that there is often a very large gap between the kind of analytical capabilities that you have and what you can actually do in the field. And you also have the additional challenge of convincing policymakers about how to best use the impact evaluation techniques. So as people working in policy areas, your real challenge is going to be the application of these techniques in the context of actual program implementation. So moving to the context, why are we interested in evaluation techniques? The context in which I want to present the evaluation methods is this. We have huge investments taking place in rural development programs of different kinds today in India. We have poverty alleviation programs. We have skill development programs. We have public works programs. The NREGA program, for example, is perhaps the largest public works program in the world, and it has an annual outlay of, perhaps more than 50,000 crores. So we have a huge range of development interventions, and we spend huge amounts of money on those interventions. So there is, or at least there ought to be, a substantial policy interest in knowing how effective these programs have been in achieving their objectives. So we need to know what works, what does not work. Can we look at alternative designs for these interventions? Can we achieve the same outcomes at a lesser cost? So these are the kinds of questions that we are interested in, we would like to answer. So my first brush with evaluation questions came about when in the early part of my career as a civil servant, I was posted as the project officer for the Integrated Tribal Development Project in an area of Kerala, which is close to the place called Silent Valley. So in the early 80s, the flagship program for rural development used to be a program called the Integrated Rural Development Program, IRDP. And it was a poverty alleviation program. And the underlying assumption in that program was that people are poor because they lack assets. And if you can transfer productive assets to the poor, they can come out of poverty. So the program used to provide a mix of loans and subsidies to enable beneficiaries to come out of poverty. And for the scheduled tribe beneficiaries, the subsidy used to be 50%. Now, my experience of implementing the program was that from a governmental perspective, most of the focus was on achieving targets. Have you met the targets for loan disbursement? Have you met the targets for subsidy disbursement? Only very occasionally, the government would want an evaluation of the program. But even then, the focus used to be on whether beneficiaries had misutilized the assets, had they sold off the assets without repaying the loan. So we would often get a missive from the state government saying we need to strictly monitor all the IRDP beneficiaries. So we would then get into our jeeps and with our team of people and go from beneficiary to beneficiary, checking whether they still had the assets. So what we would find generally was quite interesting. Firstly, we would find that for most beneficiaries, there was no apparent difference in the poverty status or income after they had taken the loan. We would find that a good proportion of beneficiaries no longer had the assets purchased, say, 6 months after the loan. Maybe they lost them, maybe the milk animals died, or maybe they sold it off. And interestingly, some of the beneficiaries who had sold off the assets appeared to be better off in terms of consumption. So what could we conclude about the effectiveness of the program in poverty alleviation? The point was that in this kind of a context, we really had, as field level functionaries, no capacity to carry out a systematic evaluation. Now, of course, we have a fairly elaborate system of the audit of government expenditures in government departments. So, for example, the programs of the Rural Development Department will be audited by the Comptroller and Auditor General. We will have legislature committees looking into the programs, and sometimes evaluation is carried out by specialized units at the state or central government levels. Many states have state planning boards which carry out these evaluations. But most audits examine or focus their examination on the processes that are employed. Was the money spent in accordance with the prescribed procedures? Were the beneficiaries selected as per the norms? Was there an overspend or underspend? So the focus used to be on what we call propriety audit. Now, very few of these audits really raise the question of whether the program has achieved its objectives. So did the beneficiary come out of poverty? That is not really a question which the C&AG's auditors would ask. So the context is that we have huge expenditures on development programs, but at the same time, there is very limited focus on what we call outcome evaluation. So, and there is very limited awareness of the need for evaluation, and the capacity to carry out evaluations are also lacking, particularly at the level of field level functionaries. So the focus of this session is on evaluation of program or intervention outcomes. So this session focuses on how we can evaluate outcomes. So I have based my lecture on an excellent World Bank publication called Impact Evaluation in Practice. And if you go to the website, which I have given here on the slide, you will find not only the manual, but also a lot of technical materials, including STATA program codes for a data set and STATA program codes for running many of the evaluation techniques. So it's an excellent resource which you can consult. And this, the book, Impact Evaluation and Practice, one good thing about that is that it focuses more on the intuition and the rationale for many of the methods that we are going to discuss. It does not really focus too much on the econometric aspects of these methods. Now, econometric aspects of these methods are, of course, important, but today we'll be focusing on the intuition and the rationale for the kind of techniques that we can use. So what is the evaluation context? So in evaluation, the challenging empirical question is, how can we understand the cause-effect relationships? And this is in the context of development interventions. So for example, we may have a microfinance program and we may want to understand, has it enabled households to come out of poverty? Or we may have a skill development program and we may want to understand, has participation in the skill development program increased the trainees' incomes? Or we may have some kind of a conditional cash transfer program, or we may have a midday meal program for school children, and we may want to understand, has it really improved their nutrition and health outcomes? So impact evaluation actually seeks precise answers to the cause and effect problems. And the question that we are interested in answering is, to what extent did the intervention and that intervention alone cause a change in outcomes? And from a policy perspective, we are interested in this because we would like to know which intervention works, what is the benefit per unit cost of this intervention and alternative interventions. Now, one thing you should note at this point, and this is a point that must have come up in earlier lectures as well, is that we cannot simply answer this question by simply observing the beneficiary's incomes before and after the loan. Say, suppose it's a microfinance loan that you're looking at. You cannot answer the impact evaluation question by simply observing the beneficiary's income before and after the loan. The beneficiary's income in the intervening period could have increased because of several other factors which are unrelated to the program. So a beneficiary takes a loan, but then in the meanwhile, the beneficiary may have received a remittance, say, from a family member who's working in the Middle East, and that may have contributed to the increase in consumption. It may not be the loan itself. So we want to identify the change in income caused by the intervention and not by other factors. So note also that we are interested in cause-effect relationships, and we are not interested just in correlations. So for example, if you if you draw up a regression between, say, the GDP and the area of forest land that is deforested, you may find that higher levels of deforestation are associated with higher levels of GDP, but that does not mean that deforestation causes increases in GDP. So we are interested in cause-effect relationships and not just in correlations. So that is an important point to note in the context of the impact evaluation techniques. So what is the evaluation question? So we want to know, what is the impact or causal effect of a program on an outcome of interest? So if it is a microfinance loan, we may want to know what is the effect of the microfinance loan on the beneficiary's income. And this equation, which I have put up here, simply means that the causal effect of a program or impact of a program which we label as delta, because that is the change in the outcome, is the difference between the outcome with the program and the same outcome without the program. So what would the beneficiary's income, what is the beneficiary's income after having taken the loan? You want to compare that with what the beneficiary's income would have been if he or she did not take the loan. So we want to compare the with program outcome with the without program outcome, but we want to do this at the same point in time. So this is the fundamental evaluation question. So P stands for the program. So P equals 1 means the beneficiary participates in the program. P equals 0 means the beneficiary does not participate in the program. So we want to understand what would the beneficiary's income have been if the beneficiary had not participated in the program, and compare that with the beneficiary's income which we observe after participation in the program. Now, this in fact leads us to what we can call the fundamental problem of evaluation. Now, the fundamental problem of evaluation is that we observe the beneficiary with the program intervention, but we do not observe, and we cannot observe the beneficiary's income without the program intervention at the same point in time. That is because the beneficiary either participates in the program or does not participate in the program. So we cannot have a beneficiary simultaneously participating and not participating in the program. So the fundamental problem is that we never observe the same individual with and without the program intervention at the same point in time. So in impact evaluation, that is what is known as the fundamental problem. So this then highlights the need for what we call a counterfactual. So if we cannot observe the outcome for the same individual with and without the program at the same point in time, then we need to estimate or find a good proxy for what the outcome for the beneficiary would have been in the absence of the program. So we need to compare the beneficiary with some kind of a clone. So some individual who shares all characteristics with the beneficiary, except that that person did not participate in the program. So in order to find a counterfactual, we need to find a proxy or a clone who has got the same characteristics as the individual, the only difference being that the individual did not participate in the program. So for impact evaluation, what we need to do is to find a valid counterfactual or control group. So this is the fundamental problem in impact evaluation. So before we proceed further, it is important to note two types of counterfactuals which are very inappropriate to use in impact evaluation. And this is something which I'm sure must have been covered earlier in your session on randomized control trials with Professor Chiplunkar. Now, before and after comparisons, we can take the example on this slide. Suppose we are looking at, say, the impact of a beneficiary or a farmer, say, participating in a fertilizer subsidy program. So let us assume that the beneficiary has a yield of 1,000 kilograms per hectare before participating in the program. that is the baseline yield. And after participation in the program, the yield of the beneficiary goes up to 1,100 kilos, which is shown by the point A. Now, if we simply make a before and after comparison, what we would say is that the impact of the program, that is the change in the yield, is A minus B. In this case, it is equal to 100 kilograms per hectare. But this would be incorrect. This would be incorrect because we really do not know what the beneficiary's yield would have been if the beneficiary had not participated in the program. Now, suppose the beneficiary's yield, if the beneficiary had not participated in the program, was shown by this point C. Then in that case, the impact of the program would have been A minus C. So that is the impact that can be attributed to the program. On the other hand, let us assume that in the absence of the program, the beneficiary's yield may have fallen to say a point like D. In that case, the impact of the program is much larger. It is A minus D. So when we simply make before and after comparisons, it is not appropriate because we do not know what the outcome for the beneficiary would have been in the absence of participation. So of course, we as economists, you can very well appreciate this concept that before and after comparisons are not really useful for impact evaluation purposes. But so, you know, although we, as economists, we say that before and after comparisons are inappropriate, one thing that you will find that in the context of most government development programs, this before and after comparisons remain the staple of evaluations at the field level. And this is true for most development programs. So if you have an irrigation program and you want to assess its impact, so what will the evaluation be? You will look at the yields before the irrigation program, and you will look at the yields after the irrigation program. So you will say 100 hectares have been irrigated, and as a result, the area, the yield in this, or the production in this area has gone up from so much to so much. Or similarly, if you have an extension program and there is an increase in yields, we make these before and after comparisons and deduce the impact of the program. This is conceptually incorrect because we really do not know what would have happened to the beneficiary in the absence of the program. So that is why this is incorrect, although it is still, these before and after comparisons are still widely used in the context of a lot of development programs. Now, the other type of inappropriate counterfactuals are the comparisons of simple comparisons of participants and non-participants. Now, suppose, say, you have a program for which the eligibility is that you should be a small farmer. Say you should have landholding size below a certain threshold in order to be able to participate. Now, if you want to find out the effect of this program on small farmers, can you simply compare, say, participants and non-participants? That is, can you compare, say, those who are eligible with those who are ineligible, say, large farmers? That will not be appropriate because we cannot compare eligible participants with ineligible participants because there will be large differences in their characteristics. So large farmers may have very different characteristics from small farmers. So you cannot really compare small farmers with large farmers. But even within the population of eligible individuals, can you compare, say, participating small farmers with non-participating small farmers? Now, your participant group and your non-participant group, they can be different in terms of their observable characteristics, or they can be different in terms of their unobservable characteristics. So for example, if you're comparing small farmers, say all eligible small farmers, in terms of observable characteristic, the differences could be that some small farmers have got access to irrigation, other small farmers don't have access to irrigation. So this is an observable characteristic. The unobservable characteristic would be if the participant group and say the non-participant group that you are comparing differ in terms of, say, something like ability, which you cannot observe. So because participant groups and non-participant groups differ in terms of their observable characteristics and in terms of their unobservable characteristics, you cannot simply make a comparison of the outcomes of the participant and non-participant groups and then assess the outcome or the impact of the program. And this difference between participants and non-participants in terms of their observed characteristics and unobservable characteristics is what leads to what we call selection bias. Now, the selection bias, what it implies is that a simple comparison of participants and non-participants will not give you a reliable or a robust indicator of the impact of the program. So what we need to do is to construct a valid counterfactual. And to construct a valid counterfactual, we first of all need to understand how participation in the intervention is determined. What are the eligibility rules? How are the beneficiaries selected? And the counterfactual must be similar in terms of their likelihood of program participation. That is, if you want to have a valid counterfactual or a comparison group, the non-participants should be as likely to participate in the program as the participants. So the participant and the counterfactual or the comparison group should have identical characteristics, and the only difference should be their participation in the program. That means the counterfactual or the comparison group should have the same characteristics as the participant group, and the only difference should be that one group participated while the other group did not participate. So if you don't control for the differences in the observable and unobservable characteristics, then your comparison is not valid. So, and of course, another point to note is that the only reason for the difference in outcomes between the participant and the counterfactual should be the intervention. If there are other factors at play, then again, your assessment of the impact is going to be biased. Now, what are the options that you have for generating counterfactuals? And this is something you must have already come across in the context of the previous lectures. So one option for generating valid counterfactuals is what we call experimental design. And this is what would have been covered in your session on randomized controlled trials. But randomized controlled trials, as we can see, can be quite difficult to implement. So we resort to non-experimental or quasi-experimental methods. Now, before we look at the different approaches to assessing a counterfactual, let us briefly discuss what we mean by the impact or what we mean by the treatment effects, that is the effect of a program. So when we generate impact estimates, we compare the outcomes of the treatment group with the outcomes of the comparison group. Now, when you have full compliance, that is all the units in the treatment group receive the treatment, that is they participate in the program, and all the units in the comparison group do not receive the treatment, you have what is called full compliance. And in this case, the estimated impact is what is called the average treatment effect for the population. That is, you have full compliance, and the difference which you estimate in the outcomes of the treatment group and comparison groups gives you the average treatment effect for the population. Now let us consider the question of incomplete compliance. So let us think first of all of incomplete compliance in the treatment group. That is, a program is open to say X number of eligible persons, but of these, not all choose to participate in the program. So there is incomplete compliance in the treatment group. So in this case, the change in the outcome in the treatment group reflects the effect of offering the program to all the eligible participants, with some eligible people not participating. So this is called the intention to treat effect. So this is the effect in a situation where a program is offered to a large number of people, but only a proportion of people decide to participate in the program. So the effect is what is called the intention to treat. Now, the effect of participating in the program for those who actually participated in the program, that is called the treatment effect on the treated, or the average treatment effect on the treated. Now, of course, if you have full compliance, then of course the intention to treat will be the same as the treatment effect on the treated. But if you don't have full compliance, then in that case, the intention to treat will be different from the treatment effect on the treated, because the intention to treat includes the outcomes of those who are offered the program but chose not to participate. Now, what happens if you have incomplete compliance in the treatment group as well as in the comparison group? Now, treatment group lack of compliance is that you are eligible for the program, but you choose not to participate. So that is incomplete compliance in the treatment group. What is incomplete compliance in the comparison group? The incomplete compliance in the comparison group, that occurs when someone who is not eligible to participate manages to participate in the program. So let us say a person is above the poverty line, but manages to get included in the below poverty line list and therefore participates in the program. So if people who are not eligible to participate in the comparison, the non-participants, and they participate by some means, then that leads to incomplete compliance in the comparison group. In such cases, what we estimate is what is called the local average treatment effect, or LATE. So that gives you the impact for a specific subgroup of the population. And of course, this effect may not hold for other groups in the population. So for example, when you conduct a randomized control trial and you have non-compliance both in the treatment and the comparison group, the effect that you estimate is what is again the local average treatment effect. That is, it is the treatment effect for the subgroup of those who comply, both in the participating group and in the non-participating group. That is, those who will take up the program if they are assigned to the treatment group, and those who will not take up the program if they are not assigned to the treatment group. So when you conduct a randomized control trial and you have non-compliance both in the treatment group and the comparison group, what you are effectively estimating is what is called the local average treatment effect, which is the impact of the program for a specific subset of the population, in this case for the group of compliers. So let us then move on to the different approaches that you can use for construction of the counterfactual. So when it comes to the approaches, the first approach that you have already looked at is randomization. So I will not really go into the details of the randomization methods, because this has been covered quite extensively, I think, in your earlier session. Then you have instrumental variables. Then you have a method which is called the regression discontinuity design. Then you have difference in difference methods. And then you have propensity score matching. And these are the methods that we will be looking at in the course of this session. Now, although we will be not looking at randomization, it is useful to understand the advantages of randomization. So in randomization, as you would already know, individuals are selected randomly for participation in the intervention. And the main advantage of randomization is that when you have randomized selection, selection bias is by design 0 on average. So the participants and the non-participants on average will have the same characteristics, both observed characteristics and unobserved characteristics. So the treatment and comparison groups can be expected to have similar observed and unobserved characteristics. And in some senses, this randomization is considered to be the gold standard for evaluation of impact. Of course, that is also a matter of a debate, but it has got a number of advantages, because by design, it eliminates any kind of selection bias. Now, it may also be a way of distributing limited resources in a way that is perceived to be fair by the beneficiaries. Suppose you have 100 beneficiaries, potential beneficiaries, but you have, say, funds only for 50 beneficiaries, then randomized selection may at least appear to be fair to the beneficiaries. You draw a lottery, or you have some other way of generating random numbers and select the participants. That is likely to be perceived as fair. And this can be quite useful in some contexts, because in a developing country context, you will always find that there are a lot of pressures for selection of certain groups or individuals based on a whole range of other considerations. It can be based on political affiliation, caste, or tribe, or whatever. So in that kind of a situation, if you can actually do a randomized selection, it will be perceived as fair. But of course, randomization, as you would have already seen, involves a lot of disadvantages. Firstly, there are ethical issues. So, when there are a lot of people who are in need, is randomized selection really an ethical thing to do? So if there are, say, 100 children suffering from malnutrition, and you have identified those 100 children, is it appropriate to select the children based on, say, randomized selection rather than based on some indicator of, say, the extent of malnutrition? And of course, the randomized experiments can be run for pilot scale implementation of projects, but it is sometimes difficult to generalize the effects that you receive, you derive from randomized estimations to the general population as a whole. So sometimes the external validity of the impact assessments from randomized control trials, that may be questionable. But the most important constraints are really political constraints. So it is very difficult to convince particularly politicians that randomization is an appropriate approach. So I was once involved with a program for distribution of power tillers to small farmers in Kerala. And there had been a lot of controversy that, previously the selection had been made, on various other considerations. And so the minister was very keen to have a fair system of distributing or selecting the beneficiaries. So I suggested to the minister that we could go in for randomized selection from the group of eligible participants. So, and to my surprise, the minister immediately agreed. And and I was quite sort of pleased with myself. But a few days later, the minister came back to me and said, your suggestion is very good, but I don't think I can run it past my party people. So let us do one thing. I will give you a list for the selection of the participants. You can randomly select the non-participants. So that gives you an illustration of the kind of difficulties you run into when you try to convince politicians that you should go in for randomized selection. On another occasion, I was told by a very senior politician that my ideas were very good, but he had not become a minister, or the voters had not voted him into power for making randomized selection, to programs. So politically it becomes quite difficult. And the other kind of danger which is there with randomized control trials is that you think you are making a randomized selection, but even within this randomized selection, some kind of selectivity can creep in, which you may not be aware of. So, but the most important set of difficulties with randomized control trials is that they are not really acceptable to a lot of policy makers. Now, randomization cannot be applied, as is most often the case, when you have either imperfect compliance. Of course, when you have imperfect compliance, you can still estimate the local average treatment effects, or you have voluntary enrollment. That is, people can choose whether they participate in the program or not, or you have a universal coverage. So if everyone is participating in the program, then you don't have a comparison group. So when you have voluntary enrollment or you have universal coverage, you cannot really use randomization. So let us look at the first of these methods, which is the instrumental variables method. And for those of you who have a good background in econometrics, you will already be familiar with the use of instrumental variables. So what is the general context in which we use instrumental variables? So we don't really have a randomized selection. We have observational data, and we want to estimate the effect of treatment using observational data. Now, the problem is that if you have a set of outcome variables, say increase in income, and you have a set of explanatory variables, including participation or non-participation in the program, the ordinary least squares regression estimator is known to be biased and inconsistent. And this is because of what is called the correlation between the regressor and the error term. And this happens because of two reasons. One is selection bias, which we have already seen, or sometimes you can have what is called the omitted variable bias. We will just take an example. Or you have bidirectional causality. That is, X influences Y, but Y also influences X. So you have causality running in both directions. In such a situation, you will have this problem of selection bias to deal with. Let us take an example of where you could have a selection bias. Now, suppose we want to assess the impact of high yielding varieties on crop yield. Now, this is a voluntary enrollment situation. That is, farmers can either choose to adopt high yielding varieties or they can choose not to adopt high yielding varieties. So if it is the case that farmers with greater ability, and which is an unobserved characteristics, are more likely to adopt high yielding varieties, then the increase in yield which you observe for those who are adopters will reflect the effect both of HYV adoption and the farmer's ability. But for program evaluation, we are interested in isolating the effect of HYV adoption alone. We don't want to get the effect of the higher farmer's ability. We want to know what is the effect of adopting HYVs or high yielding varieties. Now, we have a situation where farmers with more ability are firstly more likely to adopt, and at the same time, farmers with greater ability are also likely to have a higher yield. So this unobserved variable, which is ability, affects both the participation in the program and it also affects the outcome in the program. So as we said, ability affects the decision of the farmer to participate in the program. So only farmers with higher ability may decide that they can deal with the complexity of managing high yielding varieties. And farmers with ability may in any case be producing higher yields. So in this situation, we have a problem which comes from the omitted variable, which is, in this case, it is ability, because ability you are not able to observe. So when you have a situation like this, what does the instrumental variables approach do? So what we do is we identify variables that affect participation in the program, but not the outcomes, that is, say, the yield. So can you think of a variable which affects the decision of the farmer to participate, but does not affect yield? So in this case, what we do is the counterfactual is derived by identifying the variation in this instrumental variable. So the effect of the program is linked to the variation in this exogenous or instrumental variable. So the approach in the instrumental variable is that you need to identify a variable that affects the treatment, that is the participation in the program, but does not affect the outcome. Now, once having identified it, let us see how you can use the instrumental variables approach. Let's just go through the steps that you will use. Now, suppose you have a regression model in which the outcome variable y is a function of x1, and this is the regressor which is correlated with the error term, and this is what is the problematic variable. So when a regressor like x is correlated with the error term, it is called an endogenous regressor. So the variation in the endogenous regressor has two parts. The part that is uncorrelated with the error term, which you can call the good variation, and that's the variation we are interested in. And the part that is correlated with the error term, which is the bad variation, which we want to remove. So the key idea behind instrumental variables regression is to isolate the good variation and then disregard the bad variation. So I'm just explaining in very general terms what is the idea behind the instrumental variables regression. So how do we estimate it? The steps. Firstly, we need to identify a valid instrument. So what is a valid instrument? A variable z is a valid instrument for the endogenous regressor x if it satisfies two conditions. One is it should be relevant. That is, the correlation between z and x should not be 0. That means z should be able to predict x. The other is what is called exogeneity. That means z and e, that is the error term, are not correlated. The correlation is 0. So this is, it should affect the participation x, but does not affect the outcome variable y. So once we have identified a relevant instrument, the method which is used is called the two-stage least squares method. This is the most common instrumental variables method that is used. And what we do is, we do this in two stages. In the first stage, we regress x on z. That is, we decompose x into two components, one that can be predicted by z, and the balance is the problematic component. And the second stage, we use the predicted value of x from the first stage regression to estimate its effect on y. So what we do is, we have identified an instrumental variable z, which we feel meets the relevance and the exogeneity criteria. We regress the endogenous regressor x on z, then use the predicted value of x from the first stage regression to estimate its effect on y. And if you, this two-stage least squares will give you an unbiased estimate of the effect of x on y. So in this case, the coefficient of x1 hat should give you the effect of the program on the outcome. Now, a few things, these are essentially econometric issues that you should note. And I don't want to really spend a lot of time, but these are just points for you to note. So when you're using the instrumental variables method, there must be as many instruments as there are endogenous regressors. So if there are k endogenous regressors and m instruments, then the regression coefficients are said to be exactly identified if m equals k, which is fine. They are supposed to be over-identified if you have more instruments than endogenous regressors, which is also fine. But it is said to be under-identified if m is less than k. That means you have lesser number of instruments than endogenous regressors, in which case you will not be able to use the instrumental variables method. Now, when you are using the instrumental variables methods, you have to have tests for the relevance. You have to test whether Z is correlated with X or not. So if Z is not correlated with X, or the correlation is very, very low, then you have what is called a weak instrument. That means Z does not really predict much of the variation in X. Then you have a weak instrument. So you have a test for whether an instrument is weak or strong. Then you can also test for exogeneity. That is the correlation between Z and the error term, is it equal to 0? Only point to note is that it is not really possible to test for exogeneity if m is equal to k. But these are essentially econometric estimation issues, but this is something that you should just note. So when you use an instrumental variables approach, you need to be worried about how many instruments you have in relation to endogenous regressors. Then you need to test for the relevance of the instrumental variable, and then you need to test for the exogeneity of the instrumental variable. Now, what are the limitations for the instrumental variables method? The biggest difficulty is that it can be very, very difficult or challenging to find an instrument that is both relevant and that is not weak and is also exogenous. And this has to be a variable which is available to you in the data set. So in instrumental variable method, you have to be really creative in finding a relevant and an exogenous instrument. And people often come up with quite weird looking instruments, which may be completely unrelated to the program in question. But this is the main difficulty. Now, the estimated effect when you use the instrumental variables method is the local average treatment effect. It identifies the effect of the program only for the subpopulation of those induced to take up the program by the instrument. So you are only able to capture the variation which is brought about by the instrument. So then, and of course, there are problems in the assessment of exogeneity that is highly subjective when the coefficients are exactly identified. That is your m equals k. Now, depending on the choice of your instrument, the magnitude of the estimated effects can vary depending on the choice of the instruments. So you can, if you choose a different instrument, you may get a different estimated effect. And of course, it is difficult to explain instrumental variables method to those who are unfamiliar with it. So randomization is quite difficult to explain to politicians. So it's almost impossible to explain the rationale behind using instrumental variables method to those who are not familiar with the method. So let us go now back to the question in our example where we talked about high yielding variety adoption and rice yields. What can possibly be an instrument? Now, and this is a data point, this is a variable which should be available in your data set. So you want an instrument which influences adoption but does not affect yield. So are there any suggestions on what could be an instrument? So you want an instrument or a variable which influences adoption but does not affect the yield. So in any case, you will have to think of these instruments, and the biggest problem is in coming up with the relevant instrument which is not weak and at the same time is exogenous. So in many of the papers on HYV adoption, what you will find is that they use variables like, suppose say the participation depends on how close to the program office a farmer is located. So access to the office which is disbursing the benefits. Then you can argue that say the distance of the farmer from the program office, that is something which affects the likelihood of participation, but does not affect the yield. So you will find in the literature, there are all kinds of instrumental variables which are used, but often it is, you have to make a pragmatic choice because you can have to live with the variables which are available to you in the data set. And you know, you may have only a limited number of variables in the data set. So it requires a lot of creative thinking, but if you can get a good instrument, then you can get a good estimate, unbiased and consistent estimate of the effect of the program. Okay, so let us then move on to a discussion of some of the other evaluation methods that you can use. The first one which I want to discuss is the regression discontinuity design. Now, this is quite a powerful instrument when you have the required data, but this is used for evaluating programs where you have a clearly specified eligibility threshold or index. That is, those who are above a certain threshold, they are eligible for the program, and those who are not below a threshold, they are eligible for the program. So regression discontinuity design uses the rule that selects an individual to a program below a certain threshold or cutoff point. So for example, if you're giving fertilizer subsidy to farmers, you may say that farmers who have less than 5 hectares of land only will be eligible for the subsidy. So you have a clear cutoff. Those who are above 5 hectares are not eligible. Those who are below 5 hectares are eligible. Now, in regression discontinuity design, you need to have certain characteristics of this threshold or index if you want to be able to use it. Now, firstly, this threshold must be a continuous or a smooth variable. That is, it should not be a dichotomous variable. So for example, if it is income, for example, can be treated as a continuous variable. But on the other hand, you cannot have a dichotomous variable, say, where you have, say, a choice between either a person is employed or unemployed. If you have only these two categories, or you have a categorical variable, say levels of education, primary, secondary, and say college education, when you have these categorical variables, then also you will not be able to use the regression discontinuity design. The other requirement is that you should have a clearly defined cutoff score. And this cutoff point should be unique to this program. Now, if you have an income threshold, for example, but that income threshold is used for multiple programs, then if you use the regression discontinuity design, you will not really be able to identify whether the effects are coming from program X or program Y, because if they have the same threshold, then it is difficult to distinguish between the effects of these programs. And of course, another requirement is that this threshold should not be manipulated by administrators or program managers or even by the beneficiaries. Now, this is difficult to achieve in practice, because we know that sometimes ineligible beneficiaries will manage to get into the list of eligible beneficiaries. So you will have incomplete compliance even in the comparison group. That is, non-eligible people will make their way to the group of participants, even though according to the criteria or the threshold, they are not eligible. So the assumption here is that participation is discontinuous at the threshold. But the counterfactual outcomes, there is no discontinuity in those outcomes. Let us take a simple example. And here the counterfactual is provided by the individuals who are just above the cutoff point who did not participate. So let us take the example. Now, in this example, which I have taken from the World Bank manual, you have a relationship between the land size holding, hectares of land, and the rice yield in kilograms or bushels per hectare. And so this regression line shows you the relationship between land size holding and rice yield. Of course, this shows that as your hectares of land increase, the rice yield also increases. Of course, I do recognize that there is a huge literature which argues that actually productivity per hectare in small farms is greater than in large farms, but this is just for the purposes of the example. So here, let us just assume that before the program intervention, this is what the relationship between land holding size and rice yields looks like. It's an upward sloping curve. Now, suppose there is a program, say, for providing fertilizer subsidy, and the cutoff for program participation is farm size less than 50 hectares. Of course, this is a World Bank example, and I realize that 50 hectares will not be a small farm in India, but let us take that for the purposes of the example. So the cutoff for the program participation is farm size less than 50 hectares. That is, if you have your land holding is less than 50 hectares, you will participate in the subsidy program. If your land holding is greater than 50 hectares, then you are ineligible to participate in the program. Now, after the program has been implemented, and for the time being, let us assume that there is complete compliance. That is, those who are eligible for the program participate in the program, and those who are not eligible do not participate in the program. So after the program intervention, the impact of the program is given by the point A minus the point B. So what we have done here is we have estimated a regression line separately for the participants, that is, who are below 50 hectares, and we have estimated a regression line separately for the non-participants. And the difference in the intercept terms, which is A minus B, gives you the estimate of the impact of the program. So A minus B is the effect of the program in terms of the increase in rice yields. So your rice yields increase by A minus B as a result of program participation. Now, one thing to note is that this estimate of A minus B is only valid for observations that are very close to the cutoff point. So in this case, the cutoff point was 50 hectares, and this assessment of impact is only valid for those who are very close to the cutoff point. It may not reflect the impact for treated units which are far away from the cutoff, say for very small farmers, say who have got less than say 10 hectares, it may not reflect. But for those who are close to the cutoff point, A minus B gives you an estimate of the impact of the program. Now, even in the when you are doing an estimation with the threshold, you can have instances of incomplete compliance. So take a look at this figure. The figure on the left shows full compliance. That is, 100% of the participants who are eligible participate, and 0% of the participants who are not eligible, they do not participate. But if you have incomplete compliance, it will look like the figure B. So here you see that those who are immediately below 50 hectares, not all of them participate. In fact, participation rises to somewhere close to 100% only when you come to very low land size. Similarly, for the those who are above the threshold, there are some who are above the threshold but still manage to participate in the program. So it is only those who have a very large land holding that their participation falls to 0. Just talking about incomplete compliance, even in the context of a regression discontinuity design. So in this case, you find that if you look at figure, the A part of that figure, that shows complete compliance. That means 100% of the people who are below the threshold, they participate, while 0% of those who are above the threshold, they participate. That means they do not participate in the program. But you can have a situation where you have incomplete compliance, and that can be seen in figure B. Here you find that some people who are above the threshold, they have managed to participate. So, the participation rate is not 0 for those who are above the threshold. Similarly, you find for those below the threshold, their participation rate is not 100%. So this gives you an instance of incomplete compliance. That is, some who are eligible don't participate, and some who are ineligible manage to participate. So when you have incomplete compliance, the RDD estimate gives you what is called the local average treatment effect. That is, it gives you the effect of the program on the compliers, that is, those who participate only if they are eligible. So that is one thing to note, that when you have incomplete compliance, the estimate that you derive of the effect is actually the local average treatment effect. That is, it is the effect of the program on the compliers, only those who participate, if they are eligible. If they are not eligible, they do not participate. Now, so one of the things that you need to do when you're applying this regression discontinuity design is to see to what extent individuals who are ineligible they have managed to participate in the program. Because if a large number of ineligible individuals have managed to participate in the program, then your estimate of the impact, which was A minus B, that is not again very reliable. Now, what you can generally do is to construct a distribution of households, say across any indicator like the poverty index. So here in the figure A, you find a distribution of the households. It shows you, the baseline poverty index on the x-axis, and on the y-axis you have the percent of households. So this is just a distribution of households across the across the whole data set. Now, if you find a fairly smooth distribution, then that suggests that there is not too much of manipulation of data. But on the other hand, if you find a distribution which looks like something on figure B, that means, at the threshold point, say at 50, if there is a very sharp discontinuity in the distribution, then what that suggests is that, yes, there has been a significant amount of manipulation. So if you find, if you have a data set and you draw a distribution of the households or the individuals, and then if you find a sharp discontinuity around the threshold point, then that indicates manipulation. So that is one way of checking whether there has been a substantial amount of manipulation, which occurs quite a lot. A lot of people who are above the poverty line manage to get included in the below poverty line lists. So manipulation of eligibility is quite common in most developmental programs, but you have to check how significant that is. Now, in terms of the interpretation of the RDD estimates, as I mentioned, the RDD provides estimates of the local average treatment effects around the cutoff or the eligibility point. And so it cannot be generalized to observations which are far away from the cutoff point. So if 50 hectares is your cutoff point, these estimates apply for those whose land holdings are around 50 hectares. It cannot be generalized to those who are quite far away from the cutoff point. So you cannot generalize this to someone who has got only 10 hectares. Now, with incomplete compliance, the estimates are valid only for a specific subgroup, that is those who comply. Now, there is also generally a question of the statistical power of the analysis, because we are essentially using a restricted set of observations around the cutoff points. So which essentially means that you require large data sets. And this is again related to the issue of bandwidth. You want a large number of observations, so you need a large data set. But sometimes in order to get a large number of observations, you may have to increase the bandwidth or the area around the threshold where you consider the observations. Now, another point to note is that the RDD design is sensitive to the functional form of the relationship between the index and the outcome. So in the example that we took, we we decided to use a linear relationship. Now, suppose the relationship between landholding size and yields is not linear. Suppose we say that there is a quadratic or a cubic kind of a relationship, then of course the estimates of impact will be sensitive to the functional form that is assumed. So one of the things to note about this RDD is that it is generally more useful for making decisions about extension of the program at the margin. Suppose your current cutoff is say 50 hectares, and you want to decide whether the program should be extended to those having up to 60 hectares of land. So if you want to make these marginal decisions at the margin for extension of programs at the margin, then it is more useful. If you want to find out about the impact of the program for the entire group of eligible participants, then RDD is not that useful, because it gives you the estimates only for those who are around the cutoff point or the threshold. Now let us look at the, and of course one advantage here is that in RDD, you don't really have to exclude any eligible units. So unlike in randomization, where you can only, you have to select people out of a list of eligibles, here it is not really, you're not required to exclude any eligible units from the analysis. So that's an advantage here. So the next method I want to look at is this difference in difference methods. Now, this method is useful when the rules of assignment to a program are not very clear. So, for example, in the previous example, we said that anyone who is below 50 hectares is eligible to participate in the program. But there are many programs where these rules of eligibility or rules of assignment to a program are less clear. Now, for example, you may take, say, there is a program for construction of rural roads. And let us say this program is taken up only in certain districts. And it is not very clear how these districts are selected, or there may be some blocks or panchayats where they are selected. And there may be no clear rules of assignments about which panchayats get this program and which panchayats do not get this program. So in this kind of a situation, you can use the difference in difference method. And what it requires is you require pre-program and post-program data for both the treatment and the control group. So you have one block which is selected for the program. The comparison block will be another block which is not selected for the program. And you need the data on the indicator variable for both the pre-program and post-program, both for the treatment and control groups. Of course, these two blocks may have different characteristics. One may be a more developed block, one may be a less developed block. But one block is participating in the program, the other block is not participating in the program. Now, difference in difference compares the observed changes in the outcome for program participants, that is for the treatment group, and the non-participating control group. So the first difference is defined as the difference in outcome before and after treatment for the participants. The second difference is the difference in outcome before and after for the comparison group. So what was the outcome, say, in the participating block where road construction was taken up? Then what is the difference in outcome for the block before and after for the block where no road construction was taken up? And the difference in difference is simply the first difference minus the second difference. So the key assumption that you make is that both blocks are exposed to similar circumstances, environmental circumstances or economic circumstances. And in the absence of the intervention, the comparison group and the treatment group would have had the same trends in outcome. That means their outcomes would have tended to move in the same way in the absence of the program. Suppose you're looking at, say, the GDP in the two blocks. What you're assuming is that in the absence of the road construction program, the trends in GDP in both blocks would have been the same. So let us take an example to see how we can compute the difference in difference methods. So this is again an illustration I have taken from the World Bank manual. Now here you have on the x-axis, you have the years. So the baseline year is year 0, and the programs is evaluated at the end of year 1. And of course, you also have pre-programmed data. You have data for year -1 and -2. And on the y-axis, you have the outcome. In this case, the outcome is the rate of employment. So there may be a program which is intended to improve the employment rate in the both in the participating unit. So how do you estimate the difference in difference impact? If you see, the first difference in this case is the before and after comparison of the treatment group. So the before and after performance of the treatment group is B minus A. So the difference between B here. Yeah, so what I was saying was that, you know, for the treatment group, the employment rate goes up from A, which is 0.60, to B, which is 0.74. For the comparison group, which already had a higher rate of employment, it goes up from 0.78 to 0.81. So in this case, what is the difference in difference impact? It is simply B minus A minus D minus C. That is the first difference minus the second difference. So DID compares differences in trends between the treatment and the comparison group. Now, because it compares the differences in trends between two different points in time, it also controls for differences in both the observed and unobserved characteristics between the two groups. But of course, these differences should be invariant over time. So we are not saying that the two blocks where we have compared the outcomes, they are exactly the same. What we are saying is that whatever observed and unobserved differences were there between these two blocks, they have remained the same over time. And if you can make that assumption, then the difference in difference estimate, B minus A minus D minus C, gives you the assessment or the estimate of the impact of the program. So in this, you are taking into account what would have happened in the comparison group, you know, both with and without the program. And so, of course, we are making an important assumption that the differences in characteristics between the two groups do not change over time. So now, if there are differences between the two groups, that is the treatment group and the comparison groups, and these differences do change over time, then the DID estimate is not very useful. So in DID estimates, we are actually assuming that the trends in both the groups would have been the same in the absence of the program participation. The levels would have been different, but the trends would have been the same. Now, how can we check the assumption of no time varying differences between the treatment and the control groups? One way in which we can do that is we can apply the difference in difference method to previous time periods, that is before program implementation. So before program implementation, the difference in difference method should yield 0 difference between the two groups. Because the program was not implemented, the trends were assumed to be similar between both the groups. So if you do a difference in difference analysis for the pre-program periods, you should get a 0 treatment effect. Then there are other ways in which you can check whether this assumption of no time varying differences between the treatment and control groups, that is valid or not. And these are called the placebo tests. So for example, if you want to check how robust your DID estimates are, then maybe you can use a fake treatment group. So for example, instead of comparing the block where where the program was implemented with a block where the program was not implemented, you can test. Suppose you take two blocks where the program was not implemented and do a DID analysis. Then again, if our assumptions are correct, you should get a 0 impact. You can also use a placebo test by using what is called a fake outcome. Now, suppose you're looking at the intervention, say, of a nutrition program on, say, child mortality. So a maternal nutrition program, which is supposed to improve child mortality. So now, if you're looking at the impact of this program, now the nutrition program is unlikely to affect the mortality of children, which may be, say, due to accidents or, say, due to other circumstances which are not related to nutrition. So here, what you can do is you can use a fake outcome. So if you use, say, instead of child mortality, you use child mortality due to accidents, say, for example, then as a result of the program, you should not really find any difference between the two groups. So you can check whether the DID estimate of differences between the two groups and the assumption regarding non-varying time differences is valid using a fake treatment, fake outcome for the groups. Or sometimes you can simply use different comparison groups and see whether you get a difference in estimates. So the main point to note here is that difference and difference estimates can be quite powerful, but you need the assumption that the two groups have no time varying differences, whether those are of observed characteristics or those or whether they are of unobserved characteristics. So note that time variant differences between treatment and comparison groups can still lead to a bias in a difference in difference estimates. So that is a fairly strong assumption that you have to make. And finally, let us look at matching methods. And some of you may already be familiar with propensity score matching methods. But the principle behind matching methods is very, very simple. So in most impact evaluation studies, data do not really come from randomized treatment and comparison groups. So you just have observational data on a certain number of units, and they're not really randomized. Now, matching involves constructing an artificial comparison group from this observational data. Now, it can be applied when there are no clear-cut program assignment rules. All that you require is a non-participant group with similar characteristics. So as long as you can get hold of a non-participant group which has got similar characteristics, which you can use matching methods to assess the impact of a program. So in matching methods, the counterfactual comes from the matched comparison group of non-participants. Now, essentially what we do is that each program participant is paired with a non-participant that is very, very similar to the participant. Now, this similarity is based on observable characteristics of participants and non-participants that are supposed to influence participation. So matching methods can really be applied only to observable characteristics. It cannot really be applied to unobservable characteristics. So in matching, you are essentially assuming that there is no selection bias due to unobserved characteristics. So conditional on the set of observable characteristics, there is no selection bias due to unobserved characteristics. So that is the fundamental assumption you are making. So this is also referred to as what is called selection on observables. So you match the participants and non-participants only based on their observable characteristics, and you assume that there are no significant differences between participants and non-participants in terms of their unobserved characteristics. Now, let us take a very simple example of matching. So here you have two groups. One is the treated units and you have the untreated units. And you are matching the treated units and the untreated units based on three variables, one or four variables. One is age, the other is gender, the third is months unemployed, and the fourth is whether they have a secondary diploma or not. So what you can see here is that this first observation is identical in terms of the characteristics to the last but one observation in the untreated units. So like this, if you are able to match the treated units with the untreated units or the participating units with the non-participating units, you can compare each participating unit with the matched unit, and the difference in outcome will give you the estimate of the treatment effect on the treated. Now, if you have got a large number of variables which influence participation in the program, and mind you, these are all variables which influence participation, then of course getting exact matches like we have in this example will generally not be feasible. So in practice, as the number of relevant observed characteristics keeps on increasing, it becomes increasingly difficult to find a non-participant who is an exact match to the participant. So you can apply this strict exact matching only in a very limited number of cases. And you may not find an exact match for each participant in the treated group, in the untreated group. So what we do is we resort to what is called propensity score matching, or PSM. Now, propensity score matching is used to construct a matched comparison of group of non-participants from a larger survey. Suppose, say, you have a survey of farmers who participated in the program, and then you have a larger survey of, say, non-participating farmers from, say, some other survey, from a larger, say, household survey. Then you can use propensity score matching to construct a comparison group. So the comparison group is matched to the treatment group using a propensity score, which is the probability of an individual participating in the program. We will come to how we estimate the propensity score in a moment. So the propensity score is the predicted probability of participation given the observed pre-program characteristics of participants and non-participants. So a propensity score is simply the prediction of probability of whether how much a participant or how much an individual is likely to participate in the program. Now, it requires good data to control for all factors that influence participation, but the advantage is it does not require randomization. It tries to mimic randomization. That means the comparison group which you construct is very, very similar to the participating group. The only difference is that the comparison group did not participate in the program. So in that sense, it tries to mimic randomization. And let us see how we can, what are the steps we need to go through to carry out PSM. So in the first step, we predict the probability of participation based on observed characteristics for participants. That is the treatment group and the non-participants, the comparison group. And this is usually done using what we call a logit or a probit model, in which the dependent variable is a 0 or 1 variable. So 0 if the person did not participate in the program, 1 if the person participated in the program. So you use a logit or a probit model to with the participation status 0 or 1 as the dependent variable, and all the characteristics that influence participation, like we saw in our example, age, gender, education, etc., as the explanatory variables which explain participation. One caution to be noted is that we should not include characteristics which are affected by the program intervention. So you should use only the pre-program characteristics. So if a program, say, improves skills of a participant, then you should not use improved skills as something which predicts participation. So use only the pre-program characteristics. Match each unit in the treatment group with units in the comparison group with the closest propensity score. So in a logit or a probit model, what you get is the predicted probability of participation. Is it 0 or is it 1? And it can be anything in between. So you match each unit in the treatment group with units in the comparison group with the closest propensity score. And the difference in the outcome for the treated unit and the matched comparison group unit gives you the impact of the program. So essentially what you are doing is you are constructing a propensity score, which is the probability of participating in the program. So you compare the units in the treatment group. Say they have a propensity score of 0.7. That is the probability of participating in the program is 0.7. With another unit in the untreated group or the non-participating group, which have got a very similar propensity score, say a score of 0.68 or 0.7. So what you are saying is that these two units are very similar in terms of their likelihood of participation in the program based on their observable characteristics. But of course, one unit participated and one unit did not participate. So the difference in the outcome between the treated unit and the matched unit gives you the impact of the program. So that is the idea behind propensity score matching. And if you take the average difference in outcome for all treated units, which are matched with their comparison group units, that gives you the average treatment effect on the treated. So a few things to note. When you estimate the propensity score for both the participants and the non-participants, you need to have a criteria for choosing what is a close propensity score. So you take one treated unit or participating unit with a propensity score of say 0.7. Now, what is a matched unit with a similar propensity score? Now, here you will find, if you go into the econometric literature on propensity score matching, that a number of different criteria have been selected. So for example, you can choose what is called the nearest neighbor. So you have a treatment unit, say with a score of 0.7, the comparison unit will be the nearest neighbor with with a score which is closest to 0.7. Or you can use a nearest neighbors or a neighbor or neighbors within a specified distance of the propensity score. So in that case, you may compare one treated unit with say 5 other matched units which have got the closest propensity score within a specified distance. Or you may stratify the propensity scores into different groups and compare the outcomes between the treatment group and the non-participant group. Then there are certain other methods which are known as the kernel probability methods. Now, what these methods do is they have a system of weighting. It is called the inverse probability of treatment weighting. What it essentially does is it is something similar to the way we use weights in survey sampling. So we use weights in such a way that the average characteristics for the treatment group and the observed group will turn out to be the same. So it makes the treatment group and the participant, the non-participant group very similar in terms of their characteristics. Now, so there are a number of different methods for determining what is the criterion for the closest propensity score. And many times you can actually try out these different methods and see how much the the average treatment effect on the treated varies. So it will vary, but it should already generally be in the same ballpark figure with these different methods. Now, one point to note is that when you compute the propensity scores for the participating units and for the non-participating units, you may find that some treated units have no matched comparison units. Like, for example, in this figure, if you see, the distribution of propensity scores is given both for the non-enrolled and for the enrolled. The enrolled are the participants, the non-enrolled are the non-participants. Now, if you look at the extreme right of the figure, there are high propensity scores for participants, but there are no such similar figures for the non-participants. So some treated units may have no matched comparison units. Similarly, some comparison units may have very low propensity scores, and there may be no corresponding treatment units with such low propensity scores. So what is normally done is that we restrict the analysis to what is called this area of common support. That is, we restrict the analysis to those units who have a propensity score in this range. This is this common support range. The arrows show you the range of common support. And when we do this, what we should note is that the treatment effect that we get by taking the difference between the treatment units and matched units and taking the average of all those, what you get is again the local average treatment effect. So that is, it gives you the average treatment effect again for a subset of units. That is, these are all only valid for those units which fall within this area of common support. Now, sometimes you may be able to combine propensity score matching with difference in difference methods. So this can help you to eliminate systematic differences between treatment and comparison groups. So what kind of steps are involved? It's fairly straightforward, but it requires data for 2 time periods for units in the treatment group and in the comparison groups. So what you do is you perform matching based on baseline characteristics, that is the pre-program characteristics. Then for each treatment unit, you compute the change in outcome between before and after periods. That is, for the treatment units, you find out what is the first difference. For each matched comparison unit, compute the change in outcome between before and after periods. So that is, you compute the second difference. And then, of course, you apply the difference in difference methods. So first difference minus the second difference. So here what you are doing is you are first matching the units based on propensity score matching, and then you are applying the difference in difference methods. And what this helps you to do is to eliminate any systematic differences, including in both observed and unobserved characteristics, just like with DID. But then you have to use PSM first to establish the matched counterparts, and after that you apply the difference in difference methods. So now the main limitations of propensity score matching: firstly, you require large data sets with data on variables influencing participation. And one problem sometimes which comes when you do these estimations is that you may have the area of common support may be very, very small. So, if the area of common support between the treated and the untreated groups is very, very narrow, then the analysis does not work. Similarly, as we have already noted, PSM allows only for differences in observable characteristics. It does not allow for differences in unobservable characteristics. That takes place only if you are able to combine PSM with difference in difference. So there is a fairly strong assumption here. No systematic differences between treatment and comparison groups in terms of unobserved characteristics that could influence outcomes. So propensity score matching is quite useful when you have data on the observed characteristics for both participants and non-participants. But we are making a fairly strong assumption that really there are no differences in terms of the unobserved characteristics. So what are the challenges for applying these techniques in practice? So as highly trained economists, I'm sure, mastering these techniques should be fairly easy for you. The problem, as I said right at the outset, is in engineering the application of these techniques at the actual program implementation level. And you will often be dealing with, although you may be a PhD in economics, you may find that the people you are interacting with, they are not econometricians. It is very difficult to, say, explain the nuances of regression discontinuity design or difference in difference methods to people who are non-economists. So the most important challenge is to convince policymakers or program managers and even field level functionaries about the need and purpose for using rigorous evaluation methods. As I said earlier, in a vast majority of government program implementation contexts, what is simply used is before and after evaluation methods. And that generally goes fairly unquestioned. But the fundamental thing which you need to convey is, explain this need for a counterfactual. Many policymakers don't really appreciate the need for a counterfactual. So when we used to go for our evaluation of the IRDP beneficiaries, we simply used to assume that they were poor because they were in the below poverty line list. And we used to observe how they are doing after they have taken a loan and how, say, for about 6 months. We never used to ask about what could have been the intervening changes in the beneficiaries' outcomes before the, after the, in the intervening period. So explaining the need for a counterfactual to policymakers is a fairly significant challenge. Now, incorporating the evaluation considerations in the design of the data collection for development interventions, that is another major challenge. So if you want to apply difference in differences, or if you want to apply propensity score matching, you need to have some kind of data, and that data collection should be designed at the intervention stage itself. Suppose you want to apply difference in differences. That means you need to collect data in the road construction program. But very often program managers and policymakers will say, I'm implementing the program in this particular block. Why should I collect data on blocks which are not implementing the program? Similarly, in most development interventions, even today, we find that there is no baseline data available. We have very little data on what the income of the beneficiary was at the start of the intervention. baseline data is not available at all. Now, data collection involves a cost. So we need to convince the program managers or the policymakers that you need to collect baseline data. You may need to collect data on not only on the treatment groups, but also on the comparison groups. So these are the kind of challenges that you will have to address. The analytical techniques can be fairly easily mastered. But perhaps the biggest constraint in applying these techniques is really the development or the lack of capacity at the state or district level for undertaking impact evaluation. So, maybe at the level of the state planning boards or at the level of Niti Aayog, you have the expertise for undertaking impact evaluation. But does your block development officer or your district agricultural officer, is there capacity at the field functionary level to undertake these evaluations? Even if they don't do the evaluation themselves, they need to have a broad understanding of the evaluation concepts, because that will then inform how they design the data collection. So if district agriculture officer is distributing, say, farm subsidies or fertilizer subsidies, and they collect data only on participants, then as you can see, you don't really have a counterfactual, you don't have a comparison group, and it becomes very difficult to apply these techniques. So when it comes to impact evaluation, the biggest constraint is the lack of capacity at the state level or the district level, particularly at the level of field level functionaries. So can you explain to a local panchayat president why you are collecting information on people who are not participating in the program? So that is the kind of challenge. So development of capacity in field level functionaries, I think that is very, very important. And one area where it is particularly important is in implementing evaluation designs, particularly when you are applying selection algorithms. So for example, let us say you are extremely fortunate and your program manager or your policy maker has agreed for randomized selection, or to undertake a randomized control trial. Will the field level functionary know how to do a random selection of beneficiaries? So how do they have the kind of understanding of the algorithms? Do they have a kind of access to a sampling frame? So those types of issues are really the challenges in evaluation in practice. But for a group of well-trained economists, I think these analytical techniques, I'm sure most of you are perhaps already familiar. The real challenge you have to think about is how you can translate your analytical skills, or sort of bring it down to the level of the actual implementation of programs. So I'll leave it at that here.